Hey YouTube, it's Dimitri, and today I wanted to do a little bit of fun with math here. So often we think quant finance is way too complex mathematically, and there are really cool, fun things you can do with simple math here, right? You don't need college level, graduate level math a lot of times to do what we're doing. You just need a really strong understanding of math and kind of the problem we have and how we're going to solve it. So today we're going to play with polynomials. Okay, so a polynomial is nothing more than basically a variable. So we're going to have some sort of coefficient here. I'm going to call them A, B, C, D, and so on. And these are going to represent our coefficients. And then we're also going to have a X variable here. And the X variable is going to be raised to some sort of power n. So quite simple, just like you learned in high school. And we're going to structure these in a way such that we're going to have like A times X to the first power. So you don't even need to write the 1, but plus, B times X squared plus, and we're going to go all the way out and we're going to do, I don't know, I'll call it Z just for fun here. Hopefully we don't have 26 of these, but it's going to be X to the N here. In this case, if you had alphabetical, this would be 26. And then before we get going too far here, I want to just kind of make a few notes for those of you that have forgotten polynomials. I know I don't use them very often, but when I do, I have to go back and look up these super simple things. When we have a function, for example, like X squared, if you recall correctly, it's going to look like this. It's going to be centered around the mean. It's going to be symmetrical. And the fact that the power here is going to be even means that both ends of these are going to be going in a single direction here. There's also a sign here. So this is technically positive. The positive is going to be the direction. So the fact that it's positive means that we're going to have the directions going up. So in this case, we have an up arrow here and an up arrow here. The fact that we have a positive here as well means that they're going to go in the same direction. So when your exponent is even, this is going to be the same direction. So in this case, this is going to represent, like I said, this is just X squared. Now, if you had negative X squared, you would have almost the exact same chart, except for the fact that we're going to have these arrows again going in the same direction because our exponent is even, but the sign is negative, which means these arrows are going to be pointing down. Now, when you have an odd portion of here, so you have an odd exponent, these arrows are just going to go in the opposite direction. So as an example of this, if you have X to the third, it's going to look something like this. So you can see in this case that the arrows themselves are going to go in opposite directions. One is going up and one is going down. Now, again, this is positive. So if we wanted to flip this, so this is a positive case here. So we're going to pretend it's positive. I don't need to write the positive, but you'll have, again, the inverse case here where it goes through the origin. And again, since we have negative X to the third here is just indicating that these arrows on the ends are going to go in opposite directions. And then the negative piece is going to flip this around the x-axis, the horizon here. So we saw that in this case as well. This was the x-axis, the x squared flipped over the horizon. So just a quick introduction on these kind of pieces of this. So let's look at a quant finance example here. And it's important to note, we kind of have two states here. We're going to have discrete and we're going to have continuous. We're actually going to start with discrete and then we're going to move into continuous and then I'm going to go back to discrete here. So continuous is amazing for a variety of reasons. The fact being we have every single data point. But often when we're looking at things in quant finance, we're going to be working in the discrete space in the sense that let's give this example here. I got this from, being at the Princeton conference here. I was just helping a student with an interesting problem. And you might be modeling two separate things here. So, let's say we're modeling the S&P 500. In this case, this is a stock price. We can say that we have daily data. So this is daily data. And we can have, I don't know, like this is like January 1st. And let's go out to, I don't know, say December 31st. So it's one full year. And then we're going to have 252 So I'll write it here, 252 data points because there are 252 trading days in a year. This is just how the markets work here. So, you could have, again, price on the y-axis, and the stock price is going to look something like this. I don't know. We'll just make something up. But you'll notice there'll be 252 points. So even though I'm drawing this as lines, what this is really going to look like in data form is going to be something like this. And of course, there'll be 252 of them. And in your table form, you'll have something like date in this column. And then on this other side, you'll have S&P 500, and you'll have some sort of price here. So let's just say it's $100, and it might jump to like 102, and then it goes back to 101, and it goes all the way down. Let's say it ends up at $121 here. So this is just discrete, meaning we just have a data point for each point. Now, one of the problems that many students run into is that you want to use some sort of data that is not going to be the same granularity. So in this case here, we had daily data, but let's say we wanted to use something like, let's say GDP, and let's say your GDP comes in monthly. Now, the issue with this is going to equal to 12 data points where your S&P has 252 data points. And so if we did GDP on this same chart here, again, this would be a little wonky because we can't have price now. We need to have GDP. You would have something such as you'd have a price here. You would have a GDP value here. You'd have one maybe here. And so you see the issue, and many students ask the question is, how do you align the GDP, which is different granularity, with the S&P 500? And so let's define the problem really specifically. The problem is we have, different levels of granularity, and there are many ways to handle this. Let's just go through a few naive ways to do this, and then we'll kind of build up to it. Again, the way we're doing with polynomials is not the most complex. There are pros and cons of everything. But one case, which was kind of mentioned, let's say you have these 12 data points here. What you can do is the first approach is that you can just assume, some sort of value for each period. So we'll say for the month here. So what we could do is say, okay, you can pick kind of two things here. So you have to think about this as going to be before or after. And typically we'll pick after, which just means once we have the data point for January, let's say it comes out on the 1st, we're going to assume that same value for the entire month. And then when February hits, we'd assume the next value for the same month. And then when March hits, again, you'd have kind of these boxes here. Again, these lines should be the same, the same width, because you're assuming that value for the entire month. Now, this is one way to do it. The issue, though, is that you'll actually bias this. So if you're building models, decision trees will do much better here, theoretically. And the reason for this is because you end up having clustering. And it's not that the data itself is clustering, it's because you've actually biased your data and created an issue with this. So this is something we have to consider. Again, right, we think about this in time series formats. We assume there's going to be some sort of connection between these dots. And now you see that the green representations of these isn't necessarily the best idea because we have jumps, right? As we go from this point to the next point, we don't have a nice smooth line, we have a jump. So this isn't really not the best approach. Now, the second approach we could take, which is what they teach you a lot in data science, is you could do some sort of average here. So, we could do the average. I think this is a better approach. So we would take, this point here and this point here. And let's say, I don't know, this is like, say, $102. And this next one is $101 right here. And we would just take an average between the points. So when you take the average, you add, I don't know, 0.1, we'll call it x1 plus x2, and you divide it by 2. And that's going to give you x, I'm going to call it 1.5. So it's going to give you a midpoint here. So we think about this, you're going to have, this is zoomed in here. We're going to add in the middle of this exactly one data point. Okay, so now this is going to give us granularity. We went from 12, we're going to do 12 times 2. Technically it's, and then minus 1 at the end because you don't have another endpoint, but there's a way around that. I'm not going to get into the technicalities of doing that. But you can take this from 12 points to 24 points. Now, the issue with this is the fact that we run into I need 252 points. I don't need 24 points. So we're getting there, but we're not quite there yet. And so another way of doing this is you can actually, so putting a note here, you can iterate this. And this is a likely solution to this as well. So you can say, okay, I'm going to add 1 point here. I'm going to add a second point here and a second point here. So now instead of 2 points, which we went from 2 to 3, because now we have this gap, we're going to go from 2 to 5. And then you could split it again, and you can have the averages of these points. And all we're really doing is filling in the granularity here by splitting this up. So this works in some ways, but there's also going to be going back to basic math here. We have a divisibility problem. And I hope you see, as we looked at the divisibility of this, right, we went from 12 points if we added in the middle a point. And I'm going to add 1 at the very end as well. It's really a multiplicative in the sense that you can go from 12, that's what we start with, to 24, to 36. And 252 divided by 12 is going to be equal to 21. So in this case, it's divisible. But in many, many cases, it's not going to be divisible. You might have to switch it. So let's say it's a leap year or something, and we actually have 251 trading days. We have to divide by 12, right? This isn't going to be a whole number here. And in most scenarios, when you're working with different sorts of data, you run into this divisibility issue where, you know, we just can't divide out to get to the proper format here. And as you see here, we also end up with an issue of linearity. And so I'm going to put here too, this is called risk management. So everybody hates the fact that I talk about risk management so much. Risk management is nothing more than quant finance, but it's just been labeled and people think it's like a business job. But when you're building the model, it's your responsibility to say, we have a serious issue. We made an assumption, and that assumption by using this averaging approach is that we have a linear relationship between here. So again, you can do this and it might actually work. This is one approach. It's simple, it's easy, it's fast to use. But now you're actually, you know, you're forcing your linearity into this mess here. And so interestingly enough, the data science community uses this a lot, and yet you're implying linearity. So this is kind of an issue with that. I'm not going to cover this too much here, but you can also go backwards. So, you know, we did what I call forward. I'm going to call it propagation or forward development, which is the sense that we started off with 12 data points and we jumped forward to, you know, 24, you know, 36, and we could jump all the way up to 252. So that's a possibility. You can also just do division of this. So if you had 252 data points here and they were everywhere, you could just remove data points as you went. So you'd scale down. And the way you would do this is you would just pick and choose what you wanted here. So if you split it into, I don't know, 12 points, you could pick 1, 2, 3, 4, 5, and you'd go on out. But you can just do selection where you skip values, and that will give you more or less like a 252 trading day thing, and you can back it down into 12. So if you're trying to convert 252 down into 12, it's the same process essentially, but instead of creating data points by adding them in the middle with an average, we're just selecting the data points that we want here. And that's another approach to go backwards if you're needing to scale down. Now, the approach I like is the polynomial approach. And what we're going to do here is we're going to start off in discrete time. So as I mentioned with risk management, you might have a few data points here, and you can plot these out like this, and it might even look like this. But with the understanding of continuity, so the continuous piece here, we know in stochastic processes, which is all of finance, we can zoom in from here to here, and this little piece of the chart, instead of it looking like straight, it might be, you know, jagged like this. And then this is, say, I don't know, let's say this is daily. This might be hourly, and we can zoom in even further. And we can say, you know, we're going to do minutes. And of course, maybe for minutes, again, we're going to take from this piece to this piece. And, you know, when we do that, it looks flat. It looks like there's kind of like a, I don't know, like a W or a thing in there. That might actually look something like this, where it keeps going in here. So again, when we make these assumptions, we're going to have to make some sort of assumption. There's no perfect way because we don't have GDP measured on a daily value. We're trying to convert that to daily for our problem. We need to consider that there are, variance and fluctuations and crazy jumps and things that can occur in between periods here, whether it's daily to hourly to minutely, or in our case, if we went from, GDP at a monthly level down to a daily level. And so if we have, again, we could do stochastic processes here, but I think this is getting a little bit too complicated, and we don't need to go down that rabbit hole. But what we're going to do is we're going to try to get a function that is smooth, and the function is defined by a mathematical equation such that it is continuous. And what I mean by this is that we're going to have f of x. So this is the equation here. And it's going to be in the way that we can plug any value into x, and we're going to get back some other sort of value here. Now, I'll show you here in a second why that's important. But imagine that you're trying to scale this for a variety of reasons here. It's not just going from, getting that monthly data and converting it into daily data. Imagine that you want to convert it. So you want to go from 12 to 252. So that's monthly to daily. What if I wanted to take it from, 12 to, 180? Or there's another reason I wanted to take it from 12 to, 504. But what if I just want to scale this data into different time frames? Instead of daily, what if I wanted it weekly? Or what if I wanted it hourly? Or what if I wanted it minutely? Like, you want something that's flexible. And when you end up having a function such that you have these data points, right? And within these data points, we have this nice smooth function here. What we can end up doing is we can split the function into smaller and smaller increments. And so we can actually just divide the x-axis. So this is the x-axis. With this function over here, we can divide this up into infinitely smaller and smaller and smaller parts. And so kind of like we were talking about where we selected, just like 12 data points, instead of going forwards, we went backwards. And we picked 12 evenly spaced data points to get, S&P from daily down into monthly. We can actually use the same theory here and take a continuous function, which is defined at every single point across the spectrum here, and we can just pick and choose the granularity. So if I pick 12 data points from this continuous function, that'll give me monthly. In our case, that will exactly match. That means every discrete data point I have for the GDP over 12 months will get every exact match. Now, if I wanted to divide that into 24 or 36 or, 252 trading days, which would be 21 parts. Again, when you divide this out, now we're just taking more and more we're just dividing each piece smaller and smaller and smaller. And so the pieces here, instead of being, 12 months apart, these might be spaced, since instead of 12 equal parts, we would have like 24 parts, or you might have, 252 parts, or you might have even more. So that's why this function and using polynomials is super cool and fun, because it allows you to pick and choose the granularity once the curve has been fit. So again, maybe next week here, I will do an actual example inside of Python, because, everyone's using Python. And so we'll do an example inside of there. But what we're going to do is we're going to use the computer a little bit. So again, we're using our math theory, we're using a little bit of the computer. And we're going to decide, okay, we have these actual real world data points on this chart, and they're 12 points, and I need to fit a curve to that. What we're going to do is we're going to take x, which x is going to be the x-axis. So it'll be, 1, 2, 3, 4, 5, 6, 7, 8 in this case. And we're going to plug them into this function such that this function is going to be equal to, and now we're going to need to figure out a bunch of different things here. So this is where your polynomial skills come in. We need to select the number of terms in the polynomial. And we're going to do that through sample, like trial and error here. So what we're going to do is we're going to say, okay, here's the first try. So we're going to say try 1. And we're going to say, okay, we're going to have a times x. Okay, that's going to give us a line. That's all it's going to do. And then we're going to add an intercept term. I'm just going to call it alpha. And, these dots, it's going to fit something, more or less like this. not great. It's just a linear line. So, okay, this one, doesn't work. Then we're going to try, again, adding the function more complex. And we're going to say, okay, two of these firms, we're going to say A times X, which we're going to leave in here. And we're going to say, okay, plus B times X squared. And we're going to add an intercept here again. And now, because we know this function actually looks like this, just this piece of it, the B piece, when we add that to the linear piece, we might end up with something, that's something like this. Okay, so it's better, but it's not what we're really wanting. We're wanting something that looks, like this. We want this really curve here. And what we're going to do is we're going to keep going down this process until we find something. Often I find things, depending on how complex the curve is, it might be around like 8 or 9. And what this will look like is, again, f of x is equal to a times x plus b times x squared plus c times x to the third plus, and we'll keep going out until we end up with, we're going to have h times x to the 8th. So this is the 8th order. And then of course we're going to have our epsilon here. And often you'll see we end up with something like, say this pink line is the true line. We're going to end up with something that's going to be, it's going to be similar. They're going to be parts are a little over and parts are a little under. And in general, we're going to be able to fit this curve and we're going to be able to make this happen. But again, it's trial and error. And I'll show you how to do this maybe next week in Python. But that's how we actually fit the curve. Now, out of the reality of how things actually work in quant finance as well, we don't want to forget the fact that we talked about the exponents. And we said, if they're going to be even, we're going to see the arrows both going in one way. So we're going to have, either both up or we're going to have both down. Now, if we have odd, we're going to have one going up and one going down. Now, what this means is that the function is not well behaved beyond our spectrum here. So when we went back to this page, what I'm actually doing, and I'm not really telling you, I kind of waved my hands before, is that whatever I choose for X in this modeling framework, X needs to be the maximum possible value for X. So we can scale this down, but we're not gonna be able to scale this out. And the reason for that is because, as I mentioned here, the polynomials, these are infinities. So this is going to, positive infinity, and these are going to negative infinity. So when we saw our curve that looked like this and we were able to fit it, what I didn't tell you is because I chopped off, x is equal to 8 right here. Let's say x is equal to 1 for the starting point. This tail, because it's a positive, of course, is going to go in the same direction. This tail probably is going to go like this. And it's going to go into infinity here, and it's going to shoot down here to infinity. And these pieces aren't meaningful. Like I don't want them, right? This is not how the GDP goes. It doesn't crash down to infinite negative values here. So in this case, we have to take some sort of bounded condition. Now, how do I do this in practice though, is that I might end up with the sense that now I have 252 dots along this curve, right? And now I've filled them in. So I went from, 12, which is going to be monthly, and I went down into daily of just 252. Now I can use these data points here, and I'm going to assume, so again, we're making another assumption, which again, so this is risk management. This is risk. We're taking risk by making this assumption. I'm assuming that my curve fit correctly and I did it fairly well. And what that means is that now I can take this and I can plug this into an actual model to forecast the future. So since I hard coded essentially with this polynomial, and this polynomial is only going to work in this time frame, in this section that we're developing here, but it just gives me data points now. We're going to use like something like an ARIMA model. So now, honestly, I don't use ARIMA in this sense. We typically use Sorimax, which if you're not familiar, this is a seasonal, autoregressive, integrated, so it's non-stationary, difference at once becomes stationary, moving average with exogenous variables. Exogenous variables just means we're using external variables like GDP, interest rates, anything outside of the dependent variable we're modeling here. And then we can use this sort of time series here. So we're going to use time series, and we can actually forecast out the remaining pieces as we're moving forward. So if I need to know, again, that that forecast, we can use now the data in this range that we were able to capture using our polynomials, and we can use that to forecast here. Now, more importantly, statistics, quant finance is nothing more than determining the relationship between two variables or multivariate set of variables here. All that we've been doing here, again, is filling these in. Is I just want to figure out what is the relationship between the S&P and GDP. If you remember correctly here, the problem is that the granularity just didn't line up. And so by using a polynomial here, we can actually fit these data points, create a pseudo set of data for us. So now instead of monthly, it's going to be daily, and we can do this. Now, on a side note, as a final wrap up, if we wanted to go back into the stochastic framework, which I don't like to do, let's avoid it if possible. It gets overly complex. You could take this hypothetically and say you had these data points here, and instead of creating this nice, smooth, pretty polynomial, I really care about the jaggedness as I'm zooming in further and further and further. There are simulation methods you could use. So instead of when we took the average of the 2 points, we ended up with a line like this, which just connected them together. And then a polynomial gave us a smoother differentiable process here. There are ways where you could actually simulate. So you could even take the polynomial itself, and you could add onto that some sort of noise. So you could add on white noise, which is just assuming, in this case, that the model itself is correct. But when you add the noise into this, it's going to mean that there's some sort of randomness here. Now, you could choose different distributions of this. You could say this is a normal distribution. Again, you could assume it's something else like, a log normal. You could assume anything else to add noise to that data point here. So that's, if you're wanting to get more complex, which often we try to avoid complexities here. I like to just stick with the polynomial. It's nice, it's smooth, it gives me something reasonable. Again, it's not getting the linearity, we're getting some fluctuations in it, especially as the granularity is kind of diving down deeper. Now, there are other forms too. So as a final note, you can do all kinds of cool things here. I didn't mention here. You can do Taylor series, which are related to this. You can do splines. So a common, another feature of doing this is just cubic splines. You can do something like low-s. So local, it's locally weighted regression here. So you weight the data points closer to each other. There are all kinds of cool methods out there. Polynomials are not the only one. So I really encourage you guys to go out there and look at these other methods. But the key takeaway from this I want to show you is that one, we can use simple math that you learned in like high school. You don't need to use anything complex. Two here, the piece that we often miss with this is that you just need to figure out the data. So understand the data in a very specific framework here. It is very rigid. It does not work outside those bounds. But then after, we get the data generation, then we can go into, fitting some sort of regression or some sort of model to actually predict the forecast or the future kind of runs here. So, this is absolutely critical. Risk management is nothing more than understanding inference. It's understanding the relationships between the variables and then using that to do forecasting and prediction. So anyways, I hope you guys enjoyed this video. Don't forget to like, share, and subscribe. I will try to do a Python example of this in the next week or two here. So if you subscribe, hit the little bell button, cool little bell button here. If you hit the bell button, you will get notifications when the next video comes out. So anyways, thanks for your time. And as always, until next time.